Okay, let's start. Today we have our first seminar in this semester, and we are happy to have as a first speaker Oleg Antipin. And he's going to speak about exact semiclassical results for scaling dimensions of composite operators in phi4 theory. So please go ahead.
Окей, спасибо большое. Я пару слов скажу по-русски, может быть, Да, я работаю в Загребе, в институте Руджера Бошковича. Вот, и ну и сейчас, наверное, начну по-английски. Спасибо за приглашение, конечно. Мне очень приятно для вас рассказывать, то есть я ни разу у вас не был, но надеюсь, может, как-нибудь посетить вас вживую. Okay, so today I will talk about this, the title, which Dima already said. So let me just, so this talk will be mostly about some new ideas to solve conformal field theories. And as you well know, there are typically no simplifying limit. That's why they're hard to solve. But in the presence of a small expansion parameter, like 1 over n, sort of 't-Hooft-like expansion, as you will see, there can be subsectors of the CFT, as I can show, where conformal dimensions and OPE coefficients, in other words, the data which we need to specify CFT, we can compute this conformal data in the 1 over n expansion, semiclassical expansion, actually. So in this particular talk, I will show you how to compute conformal dimensions for the composite operator of the phi n. I will specify in a moment more precisely what I mean, but field to the power n, basically. And as I said, via semiclassical expansion. In this talk, I will study 2-point functions of such composite operators, but one can go beyond, compute higher point functions, also P coefficients. We can discuss. This talk will be mostly about 2-point functions. Please stop by anytime. I'm not sure about the audience, and I was supposed to be pedagogic, so I don't know the level of pedagogy I have to go to, but I hope it will be clear. So what I mean by the operators we're going to compute. So imagine your model has a continuous global symmetry with some Noether charges. I will call them n, charge or charges. And we just define composite operators charged under the global symmetry. So you see, I show you have n fields at the same space-time point, so phi to the n, basically. This operator obviously has charge n, if each field has a charge 1, for example. And these operators can be accessed via large charge expansion, which is 1 over n, 1 over charge. And this was this kind of research started from 2015 from papers by Kellerman, Orlando, Reffert, and Watanabe. And there was a lot of research done in this last 10 years, basically, in this field. I will mention connection with what I'm doing and also review a few things in this expansion, but it's a very large field, and actually I'm just going to touch upon it. Okay, but you can imagine that you can construct singlet operators which are uncharged, sort of phi and phi bar fields, positive and negative charge together. And those also will be, to the power n, sort of. And we recently generalized this a couple of months ago. We had a paper trying to use the same method, which I'm going to talk about, but for this family of operators, which are uncharged. Because so far the research was mostly about charged operators, as I said. So I will show you both cases just for pedagogy, even though I was asked to talk about this my recent research for the uncharged ones, but it will be, they have very similar structure and presentation. So I will start with the charged ones. As I said, I'm going to show you how to compute 2-point function in both cases, and you will see. So we're starting with the charged operators. And let me first show you how the semiclassical expansion will be organized, which I'm going to use. So for this, I follow slightly first the paper by Ratazzi, Sasha Monin, which some of you may know. I think he's from Moscow State, his PhD. So Sasha Monin, Gabriel Cuoma, and Gilles Badel. So they considered a model with the U1 global symmetry, which has 1 Noether charge. And as I said, we are going to consider CFT. So it's a conformal symmetry. There is no mass term, as you see, only quartic interactions. So in 4 dimensions, let's say, will be. So each field has charge 1. So the phi to the q and phi to the power q has charge q or minus q, depending on phi and phi bar. Okay, U1 charge q. Okay, to show the classical nature of the path integral, just rescale the field with a coupling lambda, square root of lambda, like this. as is typical in these approaches, plug it back here to the action, and you will see that 1 over lambda factorizes exactly overall from the Lagrangian for these rescaled fields. And now consider the 2-point function of these operators, composite operators phi q. You see, I show here, I write the textbook path integral representation of the 2-point function. You have to path integrate over the fields, insertion points. Here you see x final, x initial. These are insertions. I missed a bar here, I think 1 bar.
Excuse me, I don't see you any slides. Do you have slides somehow? There's no slides.
You don't see slides?
I don't see slides.
I do see slides.
You do see slides?
By the way.
Yeah, me too. For me, it's fine.
Sorry.
Okay, so this is this is important actually. Yeah. Okay.
Yeah. Okay.
What did you do?
Yeah. I know what's happened. So apologies.
No problem.
I pressed on the wrong.
So should I return a bit, or how should I do? Continue. Yeah. So do you see the slides now?
Yes, I see this.
Okay.
Could you
great.
show the previous one very quickly?
Yes. So I was. In the words I said, these things
basically. Yeah, I can follow. Yeah.
Yes. So the words I said, this how the operators look like basically, and as you will see, you didn't miss anything. So we're coming to that. We're defining this classical expansion. So we consider this 2-point function basically of these composite operators. They're charged under the global symmetry, have a charge q or minus q. This is the path integral representation. I rescale the field, so have 1 over lambda overall in the action, as I showed, and we are now considering this extreme of this action. You see, there is 1 over lambda. If lambda is very, very small, like we usually do for the Feynman diagrams, we have to the action will be dominated by the extreme of the action. The path integral will be dominated by the extreme of the action. Sorry. Okay. So now, what is the trick? You have to bring the insertion points here. You see, which appear downstairs. You have to bring them back to the exponent, the insertion points, so that they appear with the logarithms. You see here. I move them from the downstairs to the exponent, and I define a new effective action given by insertion points like this. And you see, the point is that we automatically see the formation of the sort of Hopf parameter coupling times charge in this case. In the QCD, for example, you always have a Hopf parameter like gauge coupling times the n, 1 over n, number of SUN, the rank of the group. So in this case, my large parameter is the charge. Eventually, I'm going to take it large. Lambda is small, so lambda q will be fixed. And this is my Hopf parameter. And if this parameter is very, very small, lambda q much smaller than 1, we will see that these fluctuations defined by the insertion points will be very, very small. So you have to, the lambda to the 4 term dominates. Phi to the 4 perturbation theory works as usual, and you expand around phi equal to 0, and you do usual diagrammatics as we do in the textbook. But you see, if lambda q becomes very, very large, these fluctuations from the insertions become very, very important and comparable to the original Lagrangian. And we have to try to find the new saddle points of this effective action. And it will be smarter in this regime to deal directly with this effective action rather than the original one. And that will be the main point of this talk, to find the new saddle points and expand around those in this regime. And that's why it's called large charge expansion, because charge has to be very, very large, because lambda is small. It's 1 over lambda here. So that the lambda q is fixed to some number. And that's the double scaling limit we're going to talk about. Lambda small, q is large, and product is fixed. It's the same actually as in QCD or in other kind of large M methods. Very typical. Okay? If there are no questions, let me proceed. So let us try to find the stationary points of this effective action. As I said, you write equations of motion. These are the insertions which appear on the right-hand side here. And in principle, you can solve them perturbatively. You solve for the fields, you plug back to the effective action, and you're finding correlator. But it's technically challenging. And actually, it's nothing really, we don't have many new progress. It's usual technique in the textbook, okay? So we're not going to do that. But this is the straightforward way to obtain the correlator. In fact, we are going to do different way. Imagine we have a fixed point. We sit exactly at that fixed point at some critical value of lambda, where theory has a fixed point, if it has one. And in this case, you know, two-point function we are looking for in the CFT has this power law form. We don't have to even discuss anything. All we need to find is these conformal dimensions of my operators phi q. They're written here, and you are done. And in fact, at the critical point, these conformal dimensions, they are physical. They are measurable quantity. They are G independent. They are scheme independent. And I write them here, where in general D dimensions, this is just classical term. It's just Q. If you want in 4 dimensions, dimension of the scalar field is 1. So our operator has dimension Q. You see, dimension is 4. So 4 minus 2 over 2 gives you Q, the classical dimension of our operator, phi Q. And this is my anomalous dimension, usually is called correction to the classical scaling. Altogether, they define the conformal dimension, right? This is the jargon. So I will just use conformal invariance to simplify the calculation, as you will see. But the results I'm going to obtain with this trick, even though they'll be valid at the fixed point, I'll show you that actually they're how to make them valid also for the non-conformal series. In fact, I'll compare even with the Feynman diagram calculation. But for now, we stay in the CFT. So our goal is to compute this conformal dimensions, as I said, for these operators. I showed you before that we have a sort of semi-classical expansion for our path integral. So we expect these anomalous dimensions, conformal dimensions, to appear in sort of kind of large charge expansion form. There are some functions here, delta k, which are just k plus 1 loop correction to the saddle point equation, which I'm going to define in a moment. And in this talk, I will show you how to compute the leading term, delta minus 1. It's just notation k minus 1. It's not so important, but that's how we define in our paper. This delta minus 1 term will be the classical term. And the first quantum correction around the saddle point will be delta 0. I'll show you how to compute these two things. But if you compute other coefficients, will be the full conformal dimension. Okay, and this is the large charge expansion, as you will see, where this is the charge, which is large. Okay, so semiclassical computation.
That's one thing. So
yeah,
here, when you write phi q, q means power, right? So it's field.
Yeah, it's power. Yeah, q is integer. Sort of imagine you have some q fields at the same space-time point. It's a power. Yeah, phi to the power q, like 3, 4, 5, 6, 7, something like that. Okay. It's okay?
Yeah.
Maybe I also have a question. Maybe I missed something. Are you considering some epsilon expansions or?
In a moment, yes, I will do it.
So you are assuming CFT, but in general, lambda is running, right?
Exactly. Yeah, lambda time. So we are going. Thank you very much. We are going to do Wilson-Fisher fixed point in 4 minus epsilon, and we are going to tune ourselves to precise value at the fixed point so that lambda does not run at that particular point. So we have a CFT in 4 minus epsilon dimension. But in general, lambda runs, of course. But so the logic will be like to tune ourselves to the fixed point, to use the power of the CFT techniques and conformal techniques, and then go back to the non-conformal result, as I'll show you in a moment, okay? But indeed, we are going to do epsilon expansion. But you can go beyond that. I'll mention this. Thank you very much. You are kind of anticipating the flow of the discussion. Thank you very much. Perfect. So yeah, so we're going to compute the usual stuff. Classical term, you have to find the saddle point, plug it to the action. This is your leading term, and the quadratic order expansion around the saddle point will give me the first quantum correction. I'll do it in a moment, but just to have in mind what we are going to compute. Okay. So semiclassical method. As I said, Sasha, Ricardo, and other people in 2019 developed the very clever method how to do it using the conformal invariance as a powerful tool. So we have a double scaling limit, as I said. Lambda q is fixed. Lambda goes to 0. Q is large. You have to tune to the fixed point. I will use perturbative one just to have some progress. In principle, it doesn't matter, but of course, non-perturbative fixed points are hard to find and hard to make progress anyway. But perturbative one will be sort of Wilson-Fisher, as you already mentioned. But it can be, for example, Bank-Zaks fixed point if you have one. So it doesn't matter. Just some fixed point you have to tune. Otherwise, you don't have a conformal invariance, of course. Then the next trick we're going to use is we're going to map the theory from the Euclidean space Rd to the cylinder, okay, R cross SD1. Why we're doing that? Because we're going to exploit operator state correspondence which is valid in the conformal field series. I'm not going to define it for you from the scratch, but basically to say that this correspondence states that operators, in our case phi to the q operators, are in one-to-one correspondence with the states they create. Operators phi q will create a state with charge q, and in CFT there's a one-to-one correspondence between operators, local operators, and the states they create. Okay, and in particular in this correspondence, the conformal dimension of the operator delta phi q, which are the eigenvalues of the dilatation charge, they will be mapped to the eigenvalues of the Hamiltonian, which are the energies. You can show it straightforwardly. I have a backup slides if you want more on this. I just wanted to save time to not introduce it. Also, I assume you heard about this perhaps. So we are after this delta phi q, but all we need to compute why this correspondence is the energy of my Hamiltonian, and if I compute the energy, I know the delta phi q. This is the trick. And as you will see in a moment, it will be much easier to compute the eigenvalues of the Hamiltonian. We will basically go to the quantum mechanical problem. But once we do that, we know the delta phi q. In the CFT, I always in the CFT. It works only in the CFT, this correspondence. Okay. So now we have to compute the energy, which means the expectation value of the evolution operator. So we are after this kind of matrix element, evolution operator. Operators create a state with charge q, as I said. So this state can be arbitrary because you can show that if you take a t infinity limit, separation between initial and final states is very, very large. Basically, this matrix element will be sort of given by this kind of form. And if t goes to infinity, you're projected to the ground state always. So as long as there is an overlap between the state you've chosen and the ground state, you are guaranteed in the t goes to infinity limit to select the ground state energy. If you select the ground state energy, it means you're computing the lowest possible dimension operator with charge q. Of course, there are many operators with charge q in a given CFT, but you are guaranteed to compute the lowest one because you're computing the ground state energy. I will comment more about this, but this is the important statement. We are computing ground state energy. And in principle, you don't know a priori which operator it corresponds, but I will show you that indeed, to double check that the energy we are going to compute corresponds to the operator phi q in the CFT. Okay. So from the point of view of the thermodynamics, we have a charge system. So you probably remember we have to work with the Gibbs grand canonical ensemble. We have to introduce chemical potential because we have a theory at fixed charge. It's not so important for me, but just clearly there's some chemical potential in a few slides from now. So just to give you context, this is, you probably remember from your university days that's how we deal with the systems at finite charge density. Chemical potential and the charge are the terms you have to add to your Hamiltonian, and it will appear, as you will see in a moment. Okay, so go back to our Lagrangian. So this is our flat space Lagrangian. We have to tune to the fixed point. In 4 dimensions, there is no fixed point, at least the perturbative one that don't exist. So we have to go to 4 minus epsilon. This is your fixed point. I tune to this value. Epsilon is very, very small, so it's perturbative. Then we have to map to the cylinder. As I said, cylinder is a curved space. So we have to make sure a conformal invariant is still intact. You have to introduce the coupling between the Ricci scalar and the phi squared, as usual, in the curved space to preserve conformal invariance. So this is the coupling. This is the value of the Ricci scalar. This is the prefactor. So all in all together, it gives you m squared. You see, you combine these results. So we have this mass term. You see, in flat space, it's massless, but in curved space, you have a mass. You have a question, Tivan?
Excuse me, is the cylinder is sphere times interval?
So sorry, say it again.
Is it a cylinder means sphere times
Yes.
interval of time?
Yes,
Oh,
yes,
okay.
Exactly. Yeah, exactly. Sorry, sort of like this.
Yeah.
Time and wrapping the sphere. Yes, exactly. So sphere is curved. So we're in a curved space. We have to introduce this coupling as usual to make it conformally invariant. Conformally coupled scalar to the Ricci scalar, and this is the result. You see, you combine all this, you plug it here. This is the mass. Okay, you agree? This is what I'm going to use. This is a mass term basically. Okay, So we are now on the cylinder. From now on, we are on the cylinder, on the curved space. We are going now to compute the classical energy, as I said, as the leading term in my semiclassical expansion. So we have a polar coordinates for my complex scalar, just for the convenience. So basically, I omit the choice of the state, how precisely choose it. But anyway, you have to basically, we compute this matrix element, as I mentioned. Sorry, you compute this matrix element. I omit some details, but I think you will not miss anything clear here. This is our effective action, remember? This is my kinetic term in these polar coordinates. This is the mass term I just showed you before, coming from this term on the curved space. This is my quartic interaction, very trivial. And this actually, this mu q term, if you remember, I mentioned, you have to introduce this chemical potential term, mu times q. You see in a moment why this term is exactly this, because mu and the charge, you will see in a moment, it's exactly this mu times q term I introduced, okay? So this is my effective action I have to work with at the finite charge density. My equation of motion stemming from this action is this here. This is for the Goldstone, for the phi. This is for the radial mode. And now you have to find the stationary solution, basically. In this case, we are going to find the standard superfluid solution. We have a system with finite charge density. And this profile looks like this. You have a constant for the radial mode, just f. And this time-dependent solution, tau, is the time on the cylinder, as you said, the time interval on the cylinder. And this mu is exactly the coefficient of my solution. It turns out to be exactly the chemical potential I need. But as far as the solution, it's just a parameter of my solution at this moment, okay? This mu. So this is my choice for the profile, for the tunnel point. And you have to fix the charge of the system, as I mentioned. As usual, the charge is defined by the zero component of the for current, right? Your for current is given by this for this U1 theory. You plug this in. Phi is given by polar coordinates. You plug phi, you plug it over here. You see that this equation gives you, left-hand side gives you m times f squared from this integral. There is a volume, 3 volume, and this is the charge. So you see the charge fixing condition boils down to this. You see, mu times f squared is exactly the charge density. That's why mu times mu f squared gives you this term. It's mu times q times charge density. You see, so this is my charge fixing condition. Okay, it fixes the system to be at fixed charge q. I call my radial mode is constant, so we don't have this Laplacian term, right? We have the usual Higgs mechanism. It's a trivial exercise. We have a Higgs mechanism-like equation of motion for the radial mode. In fact, if there will be no chemical potential, you would be doing the usual Higgs mechanism. Your mass has to be negative. Otherwise, of course, you never have a right ground state. But in this case, chemical potential acts as a negative mass, as is well known. Chemical potential drives the condensation. It's famous Bose-Einstein condensation. If chemical potential is bigger than m, this is positive. You have a positive F. So you have a Higgs mechanism at finite chemical density, charge density, and you have a Bose condensation. The system goes to the ground state. They all condense to the Bose condensed state. Okay. So this is my equation of motion for radial mode. You combine these two equations, charge fixing condition and the equation for the rho, and you have this condition. You have a cubic equation to solve. You see, it's a cubic equation for the mu. You see, automatically lambda times q appeared on the right-hand side. As we anticipated, remember, we are doing semiclassics. So only Hopf parameter has to appear if we are doing the things correctly. You see, lambda times q automatically organizes itself. This is the new coupling, in fact. We don't have a lambda or q separately. We have a lambda times q. That's how it should be. Okay, so this is my equation. You solve the cubic equation. You plug it back to the action. You define all the parameters. You see everything's defined. Mass is given by this. Remember, I showed you. You plug it back in. You obtain this leading term for the energy, which is why our correspondence gives me delta minus 1, what I call the leading approximation to my conformal dimensions of the operator phi to the power q. Okay, I called it delta minus 1. You see, we are done. And it looks like this. Powers appear because of the cubic equation. It looks a bit weird, but this is because of that equation I mentioned to you. X is just the lambda times q times 6, okay, definition. So what is the advantage of this thing? If you expand this function for the small parameter x, you start to produce Taylor series in the 't Hooft coupling lambda times q. I remind you that we are at the fixed point, so I put lambda's kind of star here to remind you that we have to be at the fixed point. So far, we are doing classical computation. I really just didn't do any renormalization, as you noticed. I really solved the classical system. I put lambda star to remind you about the CFT we have to be in, but at this level, it doesn't matter because this result is valid for any value of lambda because we are classical, nothing runs here. But I just put it for you to remember. Once we go to quantum level, it will be important to be at the quantum fixed point. But so far, it's a nuisance. And these terms, you can check exactly with the computation of the Feynman diagrams of this sort. You see, I will mention more about this, but in this regime, you are recovering the diagrammatics of the Feynman diagrams. I mentioned more about this, okay, for the small lambda times q regime. In the other regime, if you expand it, where lambda times q is much bigger than 1, you start to get this kind of expansion. And this was the large charge expansion I was mentioning before with the works by Kellerman, Reffert, and Orlando, if I mentioned. So they mostly work in this regime, not in the non-perturbative regime, where this weird powers start to appear of the 't Hooft parameter. In fact, we obtained this result in 4 minus epsilon, but they obtained this result in general dimension, general D, and using the effective field theory approach. We have an exact model in our case, right? Phi to the 4 model in 4 minus epsilon. But they obtain these results very generally using EFT techniques. In which sense? Well, I showed to you, depending lambda q is much smaller than 1, much bigger than 1, you have 2 different regimes. In one regime, your superfluid, when it's very, very small, your superfluid interacts with the light radial mode, with the pion, and all degrees of freedom are intact in your system, and you have a usual perturbative approximation to your system. Diagrammatics works, and in fact, you can compare it with the Feynman diagrams, as I will do in a moment. But if you go to lambda times q much bigger than 1 to obtain this result, it's basically to say that your radial mode starts to get heavier and heavier, and you're only left at low energy with your pion, which is phonon in this case, conformal pion. At finite density is called phonon in condensed matter literature. And radial mode decouples, and you can write effective field theory for this phonon, and this effective field theory considerations will give you these results automatically in a beautiful way. But you see the advantage of our approach. We also have a small charge regime, which is given the kind of the perturbative asymptotic, okay? But in the large charge regime, we have this formula. You don't need to have a theory. You can do EFT to obtain these results, okay? And that's what they did in 2015. Okay? So if it's, I will come back more to this, but it's just a comment on the connection to the large charge expansion. Okay, so far we obtained the leading result, the classical energy. Let me compute the first quantum correction. You have to do functional determinant as usual. So we write fluctuations around the ground state. You see, I call them pi and rho, r, basically. You expand to the quadratic order in these fluctuations. So it's shown here. So you see, if you basically see here, there is one massless mode. It's a conformal mode. It's a phonon. I just mentioned to you in the previous slide. This is the pion. Because we broke, by fixing the charge density, we broke U1 global symmetry. We have a pion. In this case, it's called phonon because we have finite chemical potential. And we have a massive state. You see here, R. It's like a Higgs. In the usual Higgs standard model, it would be like Higgs mode, the massive state. So these are the dispersion relations for these states, plus and minus, phonon and the Higgs-like state. This is my Laplacian on the sphere. Remember, we're on the sphere. So this eigenvalue to the Laplacian on the sphere. And this is my dispersions, which follow from this simple Lagrangian. This is my degrees of freedom for this theory, for this complex scalar. Now we have to basically sum the 0-point energies, which means we have to sum basically the energies given by these modes with their degeneracies, which are given by this expression on the sphere. We are on the sphere. I omit the details. Here it's used zeta function regularization in MS bar renormalization. I omit this sum will be divergent because now we are doing quantum physics. That's why here lambda star is really important, because now we really have to do renormalization because this is divergent. You have to be at the fixed point if you want to compare, for example, with the perturbative results, with the, like Feynman diagrams. The comparison will work only at the fixed point. Remember, this lambda star was like 3/10 times epsilon. So this is the point you have to compare. So I omit the results again. The small charge asymptotic will be given by this. This is my delta zero, right? This is my first correction to my energy. This is really quantum. So compare with the leading result. And you see, each term now, compared to the classical term, has one less power of Q. One less power. This will be important in a moment, okay? So this is my perturbative asymptotic. I don't show the full result of this sum. It's quite long, but you can compute it. It's in the paper of Ratatsi, you can see it, and Sasha. Okay, I just show you asymptotics. This is the small charge asymptotic. And the large charge asymptotic is quite large. I don't show it here, it's in their paper. But you can find it, okay, from this result. Let me summarize what we have so far. So we try to compute these anomalous dimensions, right, gamma, to obtain the full conformal dimension. I showed you only the first leading terms in the semiclassical expansion, delta -1, the classical term, and delta 0, the first quantum correction. And how I'm doing on time? Okay. So, and you can compare with the Feynman diagrams, as I said. To two loops, this is the result of the Feynman diagrams computation. And if you use lambda star, that fixed point I mentioned to you before, the terms I obtained here, coming from delta -1 and delta 0, you see, delta 0 has less powers of Q at each loop order. So, for example, the red terms, which are coming from these diagrams, are exactly matches these red terms from our semiclassical expansion, okay, to prove that perturbative asymptotic is correct, okay? So these are the diagrams you have to consider. This is the insertions of the operator phi q, okay? This is one loop term. You see lambda and number of external legs basically gives you power of q. Here there are 2 external legs, it means q squared. Here there are 3 external legs, it's q cubed. Here there are 4 external legs, q to the 4. And as you increase q, you also increase number of vertices. You see lambda cubed, lambda squared, lambda. So this is the series you produce, and this is exactly the series we have here. To all orders, you see, I have this red series from my semiclassics to all orders. In Feynman diagrams, you usually stop at some loop order, but here red terms, I can continue to any loop order I want, because I have the full resummed result. So it continues. So the two perturbative expansions overlap. You have a usual Feynman diagrams around the origin of the field space, and you have this large charge sort of semiclassics, and they have an overlap. My expansion goes horizontally. You see, at a given delta -1, it resums all terms of this sort to all orders. So we go horizontally. Delta 0 obtains all these terms, while the loop expansion goes vertically. This is my 1 loop, this is 2 loop, this is 3 loop. So they overlap, and in the regime they overlap. You can compare, and we did, of course. I showed you, and in fact, people obtained compared results to 4 loops, 5 loops for this family of operators, and it all works, of course. But because we can always have a lot of terms, we can compare to 5, 6 loops going horizontally. No matter how much you have loops computed, we have more, but only for this limited number of terms, delta -1 and delta 0. Okay. So this is the overlap of the two expansions. If you compute everything, of course, you compute everything. Doesn't matter, horizontally or vertically. Okay, so this was this perturbative asymptotic. What about the large charge asymptotic, the large charge expansion? I was working in 4 minus epsilon so far, but let me try to take epsilon 1, which is, of course, it's dramatic, and it's too crude approximation because epsilon is supposed to be small. But anyway, the phi to the 4 model in 3 dimensions is very important, of course. And we just use this large charge expansion I mentioned you before. So what people did, Domenico Orlando in this paper, they took this prediction from the EFT. Remember I told you they did EFT predictions. It's a very general result. You don't need a theory. These Wilson coefficients you don't know unless you know a theory. But they wrote this expansion. They fitted this coefficient to the Monte Carlo data. You see how beautifully this function fits the Monte Carlo data, showing you that the large charge expansion works actually, even with a small charge, surprisingly. Anyway, this is the large charge asymptotic in 3 dimensions. Remember, in 4 dimensions, we had 4 over 3, 2 over 3 terms. In 3 dimensions, there's 3/2, 1/2 from this general expansion. So they fitted these coefficients C3/2, C1/2 to the data, okay? And this is the result, 0.33, 0.27. We can take our results for delta -1, delta 0, in 4 minus epsilon, take epsilon to 1, and try to see how good we compare. And this is the result. You see, lowest order, which means delta -1, delta 0. Of course, we're still quite far from correct result, but as you go to the NLO, we get a bit closer to the right result. Okay. So with this, I'm going to finish about charged operators. I showed you how to compute first 2 terms and show you we can compare with diagrammatics and with large charge predictions. There is much more to be said about this. I will mention in the outlook, but unless there are questions, I will stop here with the charged operators and we'll go to uncharged operators now, family. Okay? So to have uncharged operators, let's consider the simplest theory possible. We just had U1, complex scalar. Let's remove our pion, have just radial mode. It's a 1 real scalar. It has a Z2 symmetry. There is no global symmetry anymore. It's discrete. So there is no charge. But still, I can talk about operators phi to the power n, which means n real scalars at the same space-time point. Okay. Now I call it n, not to confuse with the charge. It's just n. So this is my Lagrangian from before. Just remove all the terms with the pion, and you have what we have. This was my solution before, remember? My profile for the superfluid and charge fixing condition. And in our recent paper, a couple of months ago, with Jamal and Francesco Sanino, we found uncharged solution. Basically, in this case, we really solved equation with time-dependent profile for ρ, for the radial mode. And this solution is known actually for this equation, for the quartic equation. It gives you elliptic functions, Jacobi elliptic functions. In this case, it's Jacobi cosine function with the frequency omega and modulus kappa. They describe oscillations, of course. And before, we had to use charge fixing condition to introduce the charge. In this case, we are doing semiclassical expansion. The semiclassical quantization, in this case, will be given by the Bohr-Sommerfeld condition. There is no charge. I cannot use this anymore. But in this case, you probably remember from the quantum mechanics and the WKB approximation, the semiclassical quantization is given by this Bohr-Sommerfeld condition. The momentum squared integrated over period has to be quantized. In this case, it's 2 pi over n. So this replaced my charge fixing condition. With these conditions, you can proceed again, just like before, take the solution, plug it back to the action, and obtain delta -1, delta 0 terms. So let me just show you by comparison with the charge case to guide your eye for easier. This is my solution now compared to the superfluid. These are the parameters of the solution, x0, omega. Okay, charge fixing condition replaced with the Bohr-Sommerfeld condition. This is the period, tau. Kappa is just this elliptic integrals of the first and second kind. You solve this equation, you get this. Remember, before we solved these 2 equations to obtain connection between chemical potential and the charge. Now, from the Bohr-Sommerfeld condition, you obtain this equation, which connects lambda n. This is my Hopf parameter. Remember, lambda times n, here is lambda times q. It connects me to the kappa. And kappa defines all other parameters here, omega, x0, amplitude, frequency. They all defined by the modulus, you see. And modulus eventually link to the lambda n. So at the end, again, my energy is just function of lambda n, as it should be, okay? Just like before. So this is my energy, delta -1. Kappa now connected to lambda n through this equation. You have to solve it. It's quite complicated. I don't think you can solve it analytically, but at least you can expand and solve. And we did. Okay, so let me show you. This was our result for the charge case. Remember this cubic equation we solved? In this case, it's this. You can again expand. You use this condition from before. You expand for the small asymptotic, large asymptotic, and it works out. We checked with the Feynman diagrams, this asymptotic, and we recovered the result of the diagrams. For the large charge asymptotic, very similarly, we have again this 4/3 power, just like before, which is curious. And but the coefficient is very, very different, of course. It's some gamma functions here. It's not large charge expansion. It's completely different. But logic is very, very similar, as you see. Okay, so this is the paper we had a couple of months ago for the uncharged operators. We generalized results to the ON model for both charged and then uncharged operator from the U1 model. And also for other global symmetry cases, you can generalize, like SUN cross SUN, UCD-like series, and other global symmetries. There is no problem to do it. Also, you can generalize to other models. I talked about phi4 in 4 minus epsilon, but you can go to other dimensions. For example, you can go to 3 minus epsilon and do phi6 model, or you can go to 6 minus epsilon dimension and do phi⁵ model. It was done as well. Everything is working. So this method is very, very general. Okay. Okay. So unless there are no questions, how I'm doing on time? I have like 15 minutes, right? 15.
Yes.
Okay. Okay, great. So this I'm done about the U1 model for the charged and uncharged operators. Now I will briefly show you the paper I did with Sasha Bidnikov, Andrei Pekelner, and my other collaborators. If you want to introduce now if you have a local symmetry, not the global symmetry, but local, how would you deal with the photon, for example, in the U1 model? And we did it in our paper. So suppose you gauge the global U1 symmetry, you have a photon. The logic is very similar. You have a Wilson-Fisher fixed point, which in this case actually becomes complex at one loop. These are the fixed point values. Again, you use homogeneous superfluid ansatz, rho, chi, as you saw before. You assume 0 profile for the gauge field for the photon in this case. And because you assume 0 profile for the gauge field, in this case we recover exactly delta -1 solution for the global case. This is the same result and nothing to discuss. The corrections from the photon will appear at the first quantum level, delta 0. Okay, so again you have to expand. You have to introduce ghosts and use the Fadeev-Popov method for this theory. Expand to quadratic order. This is the ghost Lagrangian. This is my photon and chemical potential, and so on and so forth. Very similar. So all the terms without a photon are the ones I showed you before for the global case. But now you have, of course, there are much more. The photon mixes with the phonon. You see there are mixing terms and so on and so forth. Anyway, the spectrum of fluctuations, remember we are on the sphere, on the cylinder. We are on the curved space. Basically, our vector, 4-dimensional vector, can be split to the vector, and a couple of modes behave like a scalars on the sphere. You can split the vector to the nabla part and the divergent-less part. So a couple of modes of the vector behave like scalars. R pi, this is my complex scalar, the Higgs basically and the phonon. So there are 4 scalars from the point of view of the sphere. There are 2 modes which behave like a vector, and there are ghosts, of course. Okay, so on this R cross SD1 space, you have to find the functional determinant again, just like before. We did this so far for the scalar only, but now we have 4 scalars. They all mix, just like before, while the ghost and the vectors, of course, don't mix with the scalars. They have different spin statistics. So my scalars mixed. This is my 2x2 matrix before for the global case. Now it mixed with the other, with the part of the gauge field. You can diagonalize, find the dispersion relations. They're all given here. Actually, there is a gauge dependence, psi. We have to fix the gauge, of course, but it's beautifully cancels out. It factorizes it from this matrix, the psi, and cancels out in the 2-point function because of this normalization to the vacuum, z minus 1 will contain the same psi. So it comes from between numerator and denominator. So our final result, which is energy, should be gauge independent, and it does. It becomes gauge independent, which is beautiful check of our computation. So this is my spectrum of fluctuations. As I said, we have 4 scalars, a vector, gauss. You have to sum 0-point energies for all these degrees of freedom. This is my dispersions, which coming from the previous slide. You put them in, it's divergent. You have to zeta function regularize, then do MS bar normalization, and you obtain the result, which is quite complicated, as you see, and there is no point to look at this, but just to understand it's possible to do. This is your normalized result, delta 0, you see, for the gauged model now. And again, Sasha and Andrei helped us to compare, of course, these results with the diagrammatics to be sure we did everything correctly. This is my Feynman diagrams. The cross represents the insertion of the operator phi-q, and so on and so forth. You obtain it to some loop order. We did it to the 3 loop orders, and beautifully, the results we obtained from the semi-classics exactly agree. I mean, perturbative asymptotic. Of course, we can also take large charge asymptotic, but perturbative asymptotic for the small charge beautifully agrees with the Feynman diagrams. By the way, I forgot to mention that, of course, we are using conformal symmetry to tune our theory to the fixed point. But since we're comparing with Feynman diagrams, you see, Feynman diagrams don't know about the existence of the fixed point. So, of course, to compare, you have to tune to the lambda star. But as far as the result, of course, this result is valid for any value of lambda. So it's a trick. Even though we obtain conformal result, I have to write lambda star for all the results. But after I did it, I can just remove the star and claim that my result is valid for any value of lambda, just like my perturbative result from the diagrams valid for any value of lambda. So as far as MS bar result, it will be correct for any value of lambda. That's about the comment that my results, even though I do conformal techniques, are valid for also for non-conformal symmetry theories, like standard model, for example. Okay, so I forgot to mention this comment, but so to summarize, to obtain the Taylor series, I have to tune to the fixed point to use the technique. But once I obtained it, I can take epsilon to 0, forget about fixed point, and just claim that my Taylor series I obtained are valid for any value of lambda in a given scheme, of course. And that's why it works with the Feynman diagrams. Okay, this comment may be a bit obscure, but I hope it's clear. So I showed you how to do it for the gauged model. Let me just mention you can do it also for Yukawas. It's very general, there is no problem. Let's write just some Yukawa model. In this case, it's Nambo-Yonalasinio Yukawa model we did with my collaborators. I mean, some model, but again, we have a usual profile for the scalar, superfluid as usual. My fermions classically will not have any profile, just like my gauge field, photon, had no profile. And again, delta minus 1 will be given by the U1 global case result, okay? But quadratic fluctuations, you see here again, I expand to the quadratic order. Now, these are my fermions. They appear here. You have to do again the Gaussian integral to obtain my first quantum correction, determinant of the fermionic determinant, like usual, and bosonic. So this is my dispersions for the fermions. For the bosons, omega plus, omega minus, these are exactly the results I had before for the global case, remember? These are my additions from the fermions. There are NF of them. I just assume this model has NF copies of fermions. That's what we did in our paper, but it doesn't matter. And anyway, you obtain the corrections to delta 0 and delta minus 1 energies now from the Yukawa coupling. I call it G. You see, G is the Yukawa coupling. So classical energy delta minus 1 has no corrections from the Yukawa, but quantum energy delta 0 has a correction from Yukawa, and this is the result. Okay, and again, it agrees with diagrammatics, and you can check. Okay, so I showed you that the method is very general in any dimensions, in any model, many models, different interactions you can do. So at some point we did the full standard model, basically. So we said, okay, let's put the full local symmetry in the standard model, SU3 cross SU2 cross U1. Let's go to the delta minus 1, delta 0 terms, which means NLO in the semiclassical expansion. it turns out, since my Higgs field, which will be my scalar, does not talk to the gluons, to the order I'm working, to the NLO, SU3 will not enter in this calculation. It will appear only at NNLO order. So basically, we have SU2 cross UR at this order. We added fermions in full generality, the full Cabibbo-Kobayashi-Maskawa matrix, the full 3 generations of that model. Everything is realistic. And you can obtain basically the anomalous dimensions of these operators, Higgs to the power Q in this case. And this is the full result. Sorry, can you hear me? Excuse me.
Yes.
Yeah, just to make sure, because I touched my screen to be sure that I didn't screw up something. Okay, so this is the full result, full glory of the computation for the full standard model. The red terms you remember from my global case. There are Yukawa matrices here. You have hidden traces. There is a U1 coupling. This is hypercharge coupling. That's why we call them large hypercharge operators. And they all agree with the payment diagrams, as Sasha Bidnikovs was helping us to compare. It's beautiful. That's why I say that even though we use conformal techniques, our results are valid for non-conformal symmetries series, which is clearly a standard model is the example of that. And all agrees. It's just to obtain this result, we have to be tuned to the lambda star, but then just forget about lambda star and call it lambda, and this is correct. Okay, so this was the end point of that research for the computation with the hypercharge operators in the standard model. And of course, I know that Dima is interested in the Higgs explosion and multi-particle production. This was probably the main motivation to talk about my work today. So I have to, of course, make comment about the Higgs explosion. Even though I have to apologize in advance, I don't have something very deep to say. But of course, let me remind you what a Higgs explosion is. So we just mentioned about standard model. So if you have a multi-Higgs production, imagine some highly off-shell Higgs, I call it H star. From one highly off-shell Higgs, you produce n Higgses, n. And for this process, it turns out that you can consider 1 to n amplitude, and you can, at tree level, you can compute this amplitude completely. Also beyond tree level, but just to show you that amplitude for the 1 to the n process is given by this expression. You see, it's amplitude. It's not conformal data I talked before. It's not anomalous dimension of anything. It's just amplitude to produce 1 to the n from one particle, n particles. And for example, there was many papers by Jose and with other collaborators who showed, you see, because of the divergence, even of the tree level result, clearly at some very, very large n, perturbation series breaks down, and you start to see that for very, very large number of Higgses at final state, and at some point the results start to diverge, which is not very nice because this is cross section. You see, you square the amplitude, you obtain cross section, and it starts to diverge. It's unphysical, of course. I mean, how can the cross section go to infinity? But it seems to do. Of course, you have to go to next to linear order and so on and so forth. And the name Higgs explosion comes from this fact that it seems like your amplitude diverges and Higgs explode is the name. Okay, so this is the, let's say, phenomenological motivation for this direction. But what concerns us here, of course, is the similarity between this process and what I talked before. Basically, imagine if instead of Higgs, you would have a W boson in the final state. Each W carries charge 1. You have n W's in the final state. You have a finite state with charge n. And so it seems to map back to what I was talking before. You have a large charge, and perhaps you can try to use some of these conformal techniques for the Higgs explosion and multi-Higgs and multi-W story. Okay, this is the connection between the research Dima and others are doing in your group with the story I was showing here. And of course, this started in the 90s with Valery Rubakov, Dan Sean, and many other people. So what is the connection? This is my last slide, I think. Yes. What is the connection I see currently without paper from 2 months ago for the uncharged operators. There is actually there is some similarity, of course. See, it turns out to obtain this amplitude I showed you here, n factorial, Brown in 92 showed beautifully that to sum these 3-level graphs at threshold for the real scalar theory, you have to solve this basically the same equation I was solving a few slides before for my real scalar. It's the same equation of motion, of course, with some mass and the same. But differently from us, since you're talking about amplitude here, you have a process 1 to n. You see, your initial state was only 1 particle, and final state has n particles. That's why you have to have only positive frequency harmonics in your solution. You see, classical solution has only e to the I omega t because you propagate in the future. You see, initial state is singular; it's just 1 particle. That's why you retain only positive harmonics. This is the classical solution. You can check it, solve this equation of motion, and then you differentiate this solution n times, and you produce exactly the result I showed you before for the amplitude. This result is exactly given by this. It's very beautiful. It resounds to all orders, these three-level graphs. It was done by Brown. But this is the amplitude from 1 to n, as I said. You see, it's this matrix element. Field creates n particles. We studied 2-point function in conformal setup, right? So it's sort of, if you want, in this language, we do n-to-n transition. We have n particles, you see here and here, right? It's a 2-point correlator. But it's also real scalar. It's exactly the same. In addition, of course, we have a CFT to assume, but this is nuisance. But because of this n-to-n transition, it seems to me this solution, of course, is different. You see, we have oscillations, which means we have a positive and negative frequency harmonics. That's why it's different from this solution. And in fact, once the leading term of the elliptic Jacobi cosine is just a usual cosine. You can expand. And usual cosine is just positive frequency plus negative frequency, of course, as usual. It makes perfect sense because we have n to n. We have n particles in the initial state and n particles in the final state. So we have to have both frequencies. And that's why we have oscillations differently from this state. Okay? So this is the connection I see currently. But it would be very interesting, I think, to dig more in this direction and try to understand if we can do sort of end-to-end transition in the Brown language, you know, or to use some of our techniques to the explosion story. I didn't think more about this, but this is my comment about multi-particle production I see currently and how it compares to what I showed you before. With this, I conclude. I think I'm on time, right? So I just mentioned a few other things in this context, which is quite large. I didn't have time to mention many other directions. So I showed you that in a generic quantum field theory, you can compute semiclassically conformal dimensions for the phi n operators, charged to uncharged, I mean, this sort of thing, scalar to the power n, basically. And of course, I omit many aspects. For example, we resum some series. So you can ask me about the large order behavior of this series. Do we start to see some non-perturbative corrections, for example? And this, of course, is the subject of the resurgence in general in mathematical theory. So there were some papers about this by Orlando and many others. As I mentioned, you can compute higher order correlation functions, 3-point, 4-point function. It's some, of course, limited setup, but there are some papers about that in the large charge expansion. Of course, condensed matter applications are clear. We are talking about systems at finite charge density. In 3 dimensions, there are many systems like heavy ions, cold atoms, cold atoms, which are examples of the charge systems which can be described by these models. I showed you how to compute operators phi n because we chose a homogeneous ground state. Remember, we had a constant profile for the radial mode. But if you start to choose inhomogeneous ground state, which means your radial mode will start to vary with space-time, you can try to access the operators with the spin and derivatives, which means you start to insert some partial derivatives and your operators will, these are spinless operators, of course, phi to the n, but you can put ones with the spin. You can try. A bit more complicated, of course, but this is not a direction you can exploit. Also, for example, I showed you that you can compute operators in different space-time dimensions for different models. For example, phi to the 6 model, phi to the 3 model, phi to the 4 model, different dimensions. And there are certain dualities between these models. For example, phi to the 4 model and phi to the cube model is believed to be dual to each other between 4 and 6 dimensions. Using Hubbard-Todorovic transformation, you can show some dualities. So using this charged expansion, you can compare, you can compute them with the techniques I showed in both series and see if they match for the charged sector operators or uncharged, for example. So you can test dualities in this kind of series, and there are many more. So with this, I conclude. So thank you very much, and thank you for your attention. I'm done.
Thank you. Any questions? Timo?
Okay, can I ask a question? Actually, several short questions about comparison with diagrammatic calculations.
Yeah.
Do I understand correctly that you need to calculate like 3 loops in your semiclassical method? I mean, by 0 loops is the exponent, 1 loop is the exponent, and 2 loops, 3 loops, etc. Right? So you need to calculate 3 loops to completely restore the 3 loop result in perturbative calculations. Is it correct?
Yeah, you see, it's here. You see, Dima, it's here basically. For the operators I'm talking about, the 1 loop contains q squared and q typically. You see here. You see this is the loop expansion. You see here.
Yeah, but this is the exponent and pre-exponent, right? So this is kind of 1 loop semiclassical calculation.
Right, exactly. So I obtain only red terms and blue terms. You agree? You see, red terms give me this kind of terms, and blue terms give me blue term. You agree, right? You follow what it's shown here.
Yeah.
So at every loop order, you see, at every loop order, if you continue to lambda cube, I will always have a red and blue terms, which means the highest power of q and the subleading power of q, and that's it. You agree?
Yeah, but do you calculate this way 1 loop result completely?
Yes, you see, exactly. You see, I have a red term and I have a blue term. So I completely have U1 result. You see, that's why for 1 loop I completely overlap with the perturbation theory. So 1 loop is complete. You see.
So to calculate n loop result completely, you need to calculate n terms in your expansion, right?
Exactly. Exactly. You see. So for example, you see, for the 2 loops, I am missing 1 term. You see, Dim. For the 2 loops, I am missing this term. I cannot compute. This will be like delta 1 in my notation. And you see, that's shown here basically. You see, I'm missing this term. You see, I'm missing. So for the 3 loop, I'm missing 2 terms. But you asked an important question. Maybe I can mention. We call it boosting perturbation theory. You see what you can do? So I obtain some results here, for example, right? For these 2 terms.
So you can predict.
You can compute for some fixed q, like Sasha was doing, for some q from perturbative diagrams, and then do the fit and to produce the full q result. You see, and this way you can boost from known for some fixed values of q, like 1, 2, 3, which are easy to compute diagrammatically. But also knowing some general q, you can feed the unknown coefficients and to obtain the full q result. You see what I'm saying?
Yeah, I see. So a couple of other very short questions about comparison with loop calculations. So are your renormalizations of couplings are absolutely the same in MS bar scheme as in actual perturbative loop calculations?
Yes. So it's MS bar renormalization. So we do zeta function regularization. So this sum is divergent. So in this case, it's done. It's well the sphere. You see, so it's popular to use zeta function regularization to regularize the sum. But then you do MS bar renormalization, exactly like you do in the flat space. So in this sense, that's why we can compare. You have to be the same scheme. So the classical result is valid in the same scheme. There's no running, so it's classical. But to compare delta 0, you have to compare in the right scheme. In this case, it's MS bar. That's why, for example, Sasha computes an MS bar, and we compare with MS bar, and that's why it matches. Yes.
Okay, thank you. Last short question is when you restore the loop result, like we discussed now, you kind of re-expand your answer in lambda, right? In lambda. So everything that you can obtain this way is the polynomial in Q. Polynomial, actually. All you have here is polynomials in Q.
Yeah, exactly. See, so we get something like this. You see, we get
is it
something like
obvious
this.
that
Dim, it's always lambda q.
yes,
Your
yes.
coupling is like lambda q. Your plates are weird stuff, like this kind of example. But this result function, it's a result. It's all loop.
Yeah. So you.
Yeah. It's all loop.
Yeah.
But
so you automatically obtain kind of polynomials of q.
Yeah. If you expand
So
with a small argument,
an independent.
Yeah. If you expand with a small argument, this will give you the polynomial.
My question is.
Yeah. Go ahead. Sorry.
So
go ahead.
my question is, do you have? Yeah. So do you have independent kind of? Is it obvious that perturbatively that you will get a polynomial of q if you calculate like 5 loops or many loops? So only polynomial, not some complicated function of q.
You asking about perturbative computation? You asking about perturbative? Not semiclassical.
Yeah.
Perturbative. Well,
not semiclassical.
Good question. Honestly, I don't know what happens at 5 loops. I don't think ever in my life I did 5 loops for anything, but maybe Sasha can comment more about this, but it should. I mean, in the sense of comparison, this anomalous dimensions, they have a Taylor series expansion usually, in lambda. Of course, at 5 loops, I mean,
so you you kind of basically proved this non-trivial result.
Well, I mean, I would not go as far as that. Remember the 5 loop results, for example, for the phi to the q, for the phi to the 4 model. If you open papers like companies, Mikhail and others, of course, the full 5 loop result has a very complicated structure, zeta functions, of various structures. You see what I'm saying, right? So, but I think what you can generically, what I expect always happens. So, at any given loop order, you have this kind of structure. You have a q terms with the different powers of q. But the prefactors, they are very complicated, like a zeta function, some numbers, But they should be polynomial, I assume, in the sense of. But we didn't prove, in the sense, what you're asking, because I never compute, of course, full 5 loop. I only compute the leading terms. Let's say you go to 5 loops, which means you go here to the right of this diagram. You go to 5 loops. I show you only red term and blue terms, which means the highest powers at 5 loops. The red term, as you can see, it always has for this function, it always has the simple nice coefficients. There are no zeta functions here. You see like 1/2, 3/2. They're just numbers, nothing weird. The next term, the blue one, already starts to have zeta functions. You see, for example, I don't think I have it here, but you start to see zeta functions already. And that's it, basically. You see, I don't go, that's where my semiclassical ends. But if you do full perturbative result, the lower and lower powers of Q at loop orders have more and more complicated structure, which from the semiclassical point of view, it's much more and more complicated, involved computation. You see, so the highest powers of Q, if you want, they are more and more classical. You see, at every loop order, you see the logic. So they're more and more simple. And the lower powers of Q at each loop order, they're more and more complicated, they're more and more quantum, which means they're messy. Is it clear? Sasha, you have a comment, sorry, maybe Sasha can say more than me. Sasha.
Okay, thank you.
Okay. Is it possible to hear me? Do you hear me?
Yes.
Okay. So the question is regarding the perturbative calculation. It's just a combinatorial coefficient, actually. It's easy to prove in some sense. So if you show these diagrams, you see you have to put some lines inside your one particular reducible diagram. And you see
like this,
the last diagram, you have 4 lines, yes? The 4 lines inside. And this is just a leading term in combinatorial coefficients. You have to select from your Q legs, Q to the 4th, yes?
Right.
For factorial.
Actually, can I ask you about the propagators? Because if you have many lines, you have Q in the propagators downstairs. In the denominator,
this Q comes from the other selection, yes, from the selection.
You see, Dim, for example, this diagram, look at this diagram. You insert the phi Q here, the cross, you see, right? Cross.
Yeah.
So you have to select from Q legs on the, you see, imagine here Q legs incoming. You have to select two things.
Okay,
it's a combinatorial problem. To select 2 things from the Q things.
Yeah.
It will give you Q minus 1. You see, it's exactly this. Q.
Okay,
sorry.
yeah, understand.
Q times
This is
Q
not
minus
like
1. It's exactly combinatorics. This Q minus 1 is exactly number of ways to pick 2 legs from the Q legs. Right, Sash?
okay.
Yes, yes. And may I ask you a question?
Yes.
Yes, my question may be naive, but is it obvious that in this Bohr-Sommerfeld condition that you use to replace this fixed charge condition, the n that goes to the right-hand side, yes?
Yes.
Yes, is the same as this phi to the n
Of the operator.
power, yeah? Is it obvious? Maybe it's some
Not
other...
at all. Not at all. I mean, honestly, I mean...
So it's kind of coincidence or what? Or it's some physical
good question,
reason
Sash.
that this n corresponds to the state that is created by phi
right.
to the power n.
It's a very deep question. I don't have the answer. In fact, this would be very easy to understand. Of course, this is the only choice I can imagine to replace the charge fixed condition, because you have to introduce somehow n and to quantize it, right? In the sense like n has to be integer, let's say, in some meaningful setup. The only way to quantize your state is this one. If you remember, by the way, this Bohr-Sommerfeld condition, there is like n plus 1/2 here. I think it's called even Maslov correction or something. There is like n plus 1/2 here. So you see, it's like we are doing classical, here only classical result. This Jacobi function is classical. So it's like always, n plus 1/2, when n gets very, very large, n, like large charge, you can forget about 1/2 and you only keep only n here, right? So this condition is sort of classical version of the full quantum condition on the quantization of the function. So I would just imagine, for example, if you go to NLO computation, you have to restore plus 1/2 here, because this quantum correction starts to get important. But this sort of classical version to introduce something to connect, I don't see how to prove to you that this n corresponds to this n of the operator. It's a good question, but we sort of prove by comparison with the diagrammatics, and we were happy it matches. But I don't have a deep answer for you. I don't know if you're satisfied, but yeah, it turns out to be this one, at least for the classical model which we did. It matches.
Okay, thanks a lot.
Any other questions? Okay, it seems that we don't have any other questions, so thank you very much for a nice talk.
Yeah, okay, so thank you very much for the invitation.